negative, I've got negative, so it's actually positive. This goes to pi over 2 when y is positive, which gives us the 20, and it goes to minus pi over 2, which makes it go to 0 when we're negative. Yeah, anyway. Here, yeah, some of you, oh man, I was going to wipe that out. Well, that's a typo. I was going to I forgot to paint this out. Anyway, you guys can ignore it, right? To walk a mile in my shoes, haha. There you go. Where was I? So the one on the left-hand side is one of these standard trade your integral of a rational function of cosine and sine for an integral of a complex function around the unit circle. Some of you were doing something else, which involved like an infinite integral for this one. I'm not saying it's impossible, but I don't know what you're doing. So if you knew what you were doing and I just haven't seen it, but you still see it, and you think there's merit in what you did, you can come argue with me. I'll give you points back if you can convince me that it's something, you know. But I think it's easier to get those points back on the final anyway, right? So, all right, so the point is d theta is dz over iz. This is your 2. Your cosine theta is 1/2 z plus 1 over z, because that's e to the I theta, e to the minus I theta. And then we multiply through the z, and that becomes z squared. And I think I also multiplied by 2 to get rid of the half. And so when I did that, that 2 became a 4, and then the z, and then the z squared, and then that gave us a plus 1. And, you know, I can't underemphasize the importance, I mean, I can't overemphasize the importance of completing the square. If you don't know completing the square, what are you doing? But, I mean, I personally learned completing the square in differential equations. That's how stubborn I was about completing the square, because I could always do what? Solve the quadratic equation and reverse engineer it, right? At some point it hit me, oh, what I'm doing is dumb. Completing the square is easy. Why wasn't I doing this all along? What's wrong with me? I don't know. Many things. But so here we go. Z plus 2 squared minus 3, which factors like so. Only one of these is inside the unit circle, and as such matters to the calculation by the residue theorem. It's like this one here, minus 2 plus root 3. It's negative, but it's close to the 0, kind of, like minus 0.3-ish. All right, so then the residue theorem says that this is equal to that. And some of you might have used the generalized Cauchy, or the Cauchy integral formula. If so, wonderful, that's fine. Remember, the Cauchy integral formula is nothing more than the residue theorem in ugly notation. So I decided to use rule 4 because it's just 1 over something. And so I differentiated it, and that something's a simple 0. So differentiate, plug that thing in, and you get a root 3, and you got your 2 pi divided by 2. 4 pi divided by 2 gives you 2 pi. So 2 pi over 3, woohoo! Which I think is what we saw in the homework. Yes? Was this a homework problem? I know I've done it before, so it's either a homework problem. What's that?
In the notes.
It's in the notes. Did I do it in class?
I think so.
I did? I'm familiar with it from somewhere. So it's either, I don't know. I'm pretty sure this was a homework problem or a quiz problem, right? Yeah.
I recognize it.
Yeah. And so a couple of you got this. It was good. So the way to do this one, of course, is to look at the half circle contour. Notice that 2 of the singularities are inside. I'm assuming, I didn't tell you A and B were positive, did I? So you could have asked me if that was a point of contention, but I don't think anybody, no one's like, what if A and B are complex? Right? You guys are careful not to have such thoughts, right? You know, technically speaking though, you maybe should be thinking of I mean really, to be truthful, you really should be thinking of A and B as complex in this course. Although the original problem does kind of make you think they're real. I don't know. If in doubt, ask. And anyway, so, and I just, without loss of generality, I assumed A is I assumed A is greater than B, but then I wrote this diagram. What's wrong with me? Good grief. Stupid. Look at this. Duh. Anyway, it doesn't matter, but it does. All right, so then the usual estimates, triangle inequality in reverse. So the integral around the half circle goes to 0 by the ML theorem. And we just get 2 pi I times the sum of the residues, one at IA, the other at IB. And I was using rule 4 again, and then at some point I'm like, this is dumb. So I can do better. And although it does pain me to say the words do better, because I do feel like it's the siren song of morons. But so I instead chose to factor it and look at the residue, like use the, I don't know which rule it is. It's maybe like rule 1 or something, whatever it was. But essentially you just block out the offending, the singular part, the part that's 0, like for this one, I minus IA, and I put Z equal to IA, so it gives me 2 IA. And then Z squared plus B squared becomes B squared minus A squared. And on the other side, the other residue, I get 2IB from this, and then this becomes A squared minus B squared. So that's the easier way, I think, to see through the algebra. Of course, if I'd gone back to the algebra on the previous page and just stuck with it, we would have got to the same answer, you know? But this is more fun. So there it is. Hooray. Now, moving on here. This one kind of stumped you guys. I would advise probably not differentiating 5 times, but some of you, I think 1 or 2 of you got it to work. Others did not fare so well. So when I'm up against something sort of clunky like this, I just try to ask myself, how can I get a reciprocal term in Z minus 1 from what I'm given? All right, so this 2 times 2 to the Z minus 2 is really 2 to the Z minus 1. So that has this natural expansion in terms of Z minus 1. I really didn't need to write out all of that to do the calculation. I wrote all of that out to convince you what's going on, okay? That's what you're up against for that term. So how can you possibly get a reciprocal term from that? Well, depends on what you're up against. Well, you're up against this. You're multiplying by this. And so I just, I chose to add and subtract 1 because that was the easiest way to see things here. And that gave me a 45 over Z minus 1 to the 5th plus 45 over Z minus 1 to the 6th. So I'm thinking about multiplying this times that. How can I get a reciprocal term? I can only get a reciprocal term from 1 over the 5th power times a 4th power. So like this times this is going to give me a reciprocal term. And this times that is going to give me a reciprocal term. And that's it. Those are the only 2 possible ways to get a reciprocal term. That's all I need to look at in order to calculate the residue. So I did that. And that gives me 45 times 16/24 plus 32 120ths, which this one worked out better. Works out to 42. There we go. What? I'm proud of my 42s. No? I shouldn't be proud? No. Do I need to pick a new number?
No, I like 42.
I like the numbers. Yeah, 42.
Should I just always work for, always work it out to 0?
No, you should always work it out to 42.
I think he's coming from me, Jeff, because I put 0 for everything.
It was not actually targeted at you, but that's funny. All right.
I just put 0. But normally integrals are 0. It was worth a shot. Normally. What do you mean normally? It was good. Yeah. Well, that is true, I think, right? Aren't integrals often 0 in complex analysis? Well, if there's no residue.
All right. So here is test 1. You guys remember test 1? Back in the day, we had this test 1. As you go back,
Lots of problems like problem 1, please.
as you go back and look at test 1, does it seem easier now? I hope so. So, I mean, you should go back and review because these kinds of things can be on the final. Yeah. Yep, eighth roots, fifth roots, third roots. Got all your roots.
Are you gonna put the same
Something like
that
this.
we've already proven on tests on the final?
It always astounds me how students like completely ignore. Like I said all kinds of stuff here. I was like, this is the conjugate. You're given that the product of the conjugates is the conjugate of the product. Prove this. And then just this whole sentence is just ignored. Just ignored. And then people just try to do it in terms of like real variables. And it doesn't work because it's horrible in real notation and nobody gets through it on the test. But every time I teach this course and I put this question, there is always like 30% of the class who tries to do it in real notation. You know, like, so anyway, if I have a sentence about something, there's odds that it's there to help you. I don't usually give you, I mean, if it's physics, it's another story. In physics, I just give extra information because I like to see what people do with it. But, hey, did I show you guys my art?
No, you didn't.
Oh, after class, we'll show you. The other thing is, I think we have earned the right to use the multiply valued functions to solve equations where they're relevant. At the start of the course, to solve something like this, maybe you should have looked at the real and imaginary parts, made them equal, right? But there comes a point where you should use the logarithm to solve it. For me, that point was test 1. So I used the log to solve this, basically to say, oh, okay, well, 2z is an element of log I, and then that solved it for me, right? The other way to solve this would be like by specifically looking at real and imaginary parts and, you know, saying they're equal. Do you need to know definition of, you know, the three, like we had 4 different definitions for complex differentiable. That stuff still matters. Let's see here, what else? You know, but to answer your question, Anthony, I would not probably ask a proof that I haven't already asked already on a test or had said that it could be on a test. So if we go back to like test 1, I said you're responsible for these things. Those things are still responsible for, even if I didn't put them on test 1. But for test 2, well, I don't know. I mean, Jack asked for a hypercomplex problem, so I gotta. There has to be at least one.
I think you misunderstood me.
Jack came into my office, asked a question about the final. My son looked at him and said, "You're making the final harder. You know that." It's like, Daniel, you're wise. It's true. Some of you were very, very shaky on the harmonic conjugate thing. You should go back and make sure you can find harmonic conjugates. It's not a hard thing unless you don't know what harmonic conjugate means, in which case it's really, really hard. You know, let's see here. A lot of you missed problem 13. I think if you look back at that, you'll see that was something that shouldn't have happened. We should all be able to do problem 13. Either, and I didn't pin you down either. You could have used the Carr-Theodori argument that I give here, or you could have used the Calc 1 style, add 0, you know, do the limit of the difference quotient thing. That maybe you might remember from Calc 1, I don't know. You're like, I had Calc 1 in COVID, so no. I don't know. Is that right? Is that before COVID? I don't know. I don't know the timeline. Yeah. Oh, the open set proof.
Did you write that? The proper arguments given in the homework?
The what? You know, you may not argue by homework. It's funny.
That seems valid.
We proved this in the homework.
All right.
By homework example, hence proven.
All right. Well, anyway. Thanks for a great semester, you guys.
Thank you.
Thank you, Dr.
I will do my best to keep the final to the level of the class, make it interesting. exciting.
So that